In this video, I want to give you a brief introduction, brief overview of matrices from a slightly different perspective than the textbook. The textbook gives a great explanation of how matrices apply to functions. It's extremely elegant, but it might lend you to believe that matrices are defined by their relationship with functions and that is their only use. And really, that's not the case. So matrices themselves are just like numbers and vectors in that they are extremely versatile. They have many uses in mathematics, and they have their own sort of properties. Their relationship to functions, and particular linear functions, is extraordinary and extremely useful, and that's what we're going to focus on. But it's not the only aspect of matrices that you should be aware of. So in this unit, you'll see the textbook perspective, which, like I said, is very well done, but is not the whole story as far as matrices go. All right, so what is a matrix from a more general perspective? A matrix from a more general perspective is just an array of numbers. And just like a number can be used to represent things, and a vector is a list of numbers, and then a vector can be used to represent things, a matrix is an array of numbers, which again can be used to represent things. So let me give you an example. There's some notation that we need to be a little bit concerned about. So normally, well, your textbook uses bracket notation. So if I just draw just some random matrix here, like this, they use bracket notation. Sometimes you'll see the same thing written with parentheses. It all just depends on the textbook, the convention they used. I do have to admit that the bracket is pretty common. So we're going to go with the bracket notation and not the parentheses notation. But anyway, like I said, it's an array of numbers, and there's some language that goes along with this, which is sort of arbitrary. It's completely random, and you just have to memorize it. And I hate to say that because I don't like you to memorize things. I like you to understand things so that you don't have to memorize them. But in this particular case, it's just convention. It's just choices that mathematicians have made, and as a result, we have to remember what choices they've made. Otherwise, we can't communicate with them. So this matrix, it has 3 rows. We have, you can see, I mean, that's pretty obvious. There's no confusion about that. It has 3 rows, and it has 2 columns. So what we call is we say that this is a 3 by 2 matrix. We don't say that it's a 2 by 3 matrix. We say only that it's a 3 by 2 matrix. The rows come first, and the columns come second. All right. If we have something that's let's say that's a 1 by 5. 1 by 5 is 1 row and 5 columns, so that would look something like 1, 2, 3, 4, 5, like this. All right. That we would call a row vector. Anytime it's 1 column or 1 row, we call it a blank vector. In this particular case, it's a row vector. If it's something that was, say, 3 by 1, that might look like 2, 1, 7, and that is a column vector. Typically, when we represent vectors, it's almost always useful to represent the vectors as column vectors. So you'll see that pretty often. Row vectors, it's definitely, you'll see it, but it is not quite as common as, say, column vectors. Okay, so we've got that. We've got the names, but now let's talk just a little bit about the entries themselves. So let's say that I have a 2 by 3 matrix. So I might have 1, 2, 3, 5, 7, 8, something like this. 2 rows, 3 columns. So this is 2 by 3. I might label it by the letter A. It's standard to make the matrices bold, just like it's standard to make vectors bold. With a vector, we sometimes put the little hat notation over it, but this isn't a vector. So because it's not a vector, we would not put that hat notation over it. Okay, so we have a matrix there, and we have entries in them. We've got a 1, a 2, a 3, a 5, a 7, and an 8. And if I wanted to say find the entry in the second row and the 3rd column, well, then I would go over and down, and I would find that that is 8. All right. Well, we have a specific way of referring that. If we're going to say call the entries are called, say, A, they're all A something or other, A sub something. we say something like a sub 2, 3, and that refers to the entry in the second row and third column. In general, a sub ij is the entry in the ith row and the jth column. Okay? We will use this notation, this a sub ij notation, a lot because it makes it really easy to work with matrices where you don't know the entries, where the entries are variables. You can just name them all A, and then you say, okay, A sub ij is the entry in the ith row and the jth column. And you notice that I used the letter A, the capital letter A for the matrix, and a lowercase letter a for the entries. That's no coincidence. If I had called the matrix, say, B, then I might have called the entries B sub ij. And that's pretty standard. Now, you don't have to do that. You can call the entries whatever you like, but it's pretty standard to use a capital letter for the matrix and a lowercase letter with subscripts for the entries. Okay, the other thing I wanted to talk about in this video is something that the textbook sort of assumes that you know, and that's the definition of a linear function. So everything we deal with in this particular chapter, and what we're going to continue to deal with a lot throughout the rest of the semester, are linear functions. And you might think of, when you think of a linear function, you might think, oh, f of x is equal to mx plus b. That's a linear function. Well, yes, but that's a linear function in one variable. What do we mean by a linear function in multiple variables? Well, what we really mean is a function which fits two definitions, and the two definitions are this. So we say f of x is linear, and f of x, and x is a vector. So f of x is linear if and only if for all x and y, which are an element of the domain of f, and for any c, which is a constant real number, we have this. If I take the sum of two vectors and then evaluate the function at the sum of those two vectors, that's the same as doing each vector, evaluating the function in each vector individually and then taking the sum of that. Okay, that's criteria 1. And then the second criteria is that if I have take some constant multiple, some scalar multiple of a vector, and then evaluate the function at that value, that's the same as if I first evaluated the function at the vector and then multiplied by a scalar. So let's just take one quick example or a couple quick examples and make sure that that makes sense. Okay, so let's say that f of x is equal to mx plus b. So according to this, if I have f of, say, 2 plus 3, that should be the same as f of 2 plus f of 3. So let's find out is the case. So we have, what's f of 5? F of 5 is just 5m plus b. Okay, and then what's f of 2? That's just 2m plus b. And we have f of 3 is 3m plus b. And if I add those, I get 5m. Wait a second. I get 5m plus 2b. Interesting. Well, you might think I made a mistake, but actually I didn't. Because by this definition of linear function, our standard mx plus b is not a linear function. And the reason for that is because all linear functions by this definition must pass through the origin. Okay, well, this one has here a y-intercept b, and because of that y-intercept, it does not pass through the origin. Now, you'll notice that if I sort of ignored the y-intercept here, if there weren't no y-intercept, I would have gotten 5x on this side, and I would have gotten 5m on this side. It should be an m. Let's fix that. Sorry. I should have gotten 5m on this side, and I would have got 5m on this side, ignoring all the b's. All right. So that's just a word of caution that your standard linear function is not necessarily a linear function because it does not pass through the origin. All right. So now that we've seen that traditional linear functions are not examples of our current definition of linear functions, let's take an example of one that is. Let's take a function like g of t is equal to 3t I hat minus t j hat. All right. Yes, so according to this, if I have g of, say, 2 plus 3, that should equal g of 2 plus g of 3. So let's check that. 2 plus 3 is 5, so g of 5 is what we want to know on this side. 3 times 5 is 15, so we have 15 I hat, and then 5 minus 5 j hat. Okay, and then g of 2 on the other side, 2 times 3 is 6, so we have 6 I hat, and minus 2 j hat. And then we also have g of 3, and g of 3 is 9 I hat minus 3 j hat. And if I add these two, I get 15 I hat minus 5 j hat. So we see that it's the same. On the other hand, if I have g of 2 times 3, that should be the same as 2 times g of 3. Well, we already figured out g of 3. g of 3 is 9 I hat minus 3 j hat. And if I multiply that by 2, multiply that by 2, I get 18i minus 6j. And then on the other hand, if I do g of 6, that's 6 times 3 is 18i, and minus 6j. And you can see we get the same thing. Okay, so this function is in fact linear. All right, now I think you should be ready to go ahead and read the chapter and move on to the next part of the unit. Good luck.